Welcome to the lecture on solving the boundary value problem using Ritz method. So the given boundary value problem with a differential equation and two boundary conditions, and we are asked to find two parameter approximate solution using Ritz method. Right. So the solution for Ritz method depends on the weak form of the given differential equation. So we have already solved the weak form for the given differential equation. So that equation would be uh, right. So finding the weighted residual statement and perform integrating by parts, and then we will reduce the second order differential equation to first order differential equation, that is called weak form, right? So you can check out the video for weak form determination, and the equation that we have arrived is 0 to 1 dw by dx multiplied by dy by dx minus 4wy into dx plus 0 to 1 w of x dx equal to 0. So from this equation we can identify the bilinear functional and linear functional. So that would be equal to, so general form of weak form is bilinear function minus linear functional is equal to 0. Okay. So from this equation we can identify bilinear functional is equal to 0 to 1 dw by dx into dy by dx minus 4wy into dx. This is the bilinear functional. Then the linear functional, that would be equal to minus 0 to 1 w of x into dx. Okay. So uh, the Rayleigh-Ritz method, it operates on an n parameter solution. Okay, so Rayleigh-Ritz method gives an n parameter solution to the weak form equation. To weak form equation, yes, that is Vw of y minus L of w equal to 0. Okay, that is given by yn of x equal to y naught of x plus summation of k is equal to 1 to n ck pi k. So here ck is called Ritz coefficient. This is called ck is called Ritz coefficients. Ritz coefficients. Okay, and this yn of x should satisfy the essential boundary condition of the given differential equation, and any natural boundary condition is present, that is taken care by the weak form itself. So we should remember that yn of x should satisfy essential boundary condition of the given differential equation, and if any natural boundary condition is present, that is taken care by the weak form itself. Right. So non-homogeneous essential boundary condition, so we can say non-homogeneous essential boundary condition are satisfied in pi naught of x. Okay, and homogeneous form or equivalent essential boundary condition. Homogeneous form of EBC are satisfied in pi k of x. right? So let us say that the weighing function or w of x is equal to the trial function for this problem. Okay, so I is equal to 1 to up to n. Okay, in the bilinear term, the weak form. Okay, so we know that our approximate function is uh, y2 of x is equal to 1 minus x plus c1 x into 1 minus x plus c2 x square into 1 minus x. Okay, so we can say that we can replace this term bilinear function term w of y equal to pi I. Okay, so bilinear function of pi I, comma, this y is replaced by the approximate function, that is y2 of x, okay, minus linear function of pi I is equal to 0. So for our problem, I is equal to 1 and I is equal to 2. So we know that pi naught is equal to y minus x and pi 1 equal to x into 1 minus x and pi 2 equal to x square into 1 minus x. So let us do this for I is equal to 1. Okay. So for I is equal to 1, if I expand this, I should be getting bilinear function of pi 1, comma, pi naught plus c1 pi 1 plus c2 pi 2 equal to linear function of pi 1. Okay, so according to the property, according to the bilinear functional property, that is, we can say that if a linear function of alpha omega, this alpha is non-zero. Okay, so then we can take alpha outside, alpha into L into linear function of W. And similarly, if there's a bilinear function of alpha W comma Y, if again alpha is non-zero, then we can take alpha outside. So then bilinear function of W comma Y. And similarly, if bilinear function of W comma beta Y, again we can take beta outside and bilinear function of W comma Y. So which means alpha and beta are non-zero, and which means both linear in both the arguments. It is linear in both the arguments. Okay. So based on this principle, we can take the C1 common outside, C1 and C2 common. So we can say if we expand this bilinear function of pi 1 comma pi naught plus C1 into bilinear function of pi 1 comma pi 1 plus C2 into bilinear function of pi 1 comma pi 2 equal to linear function of pi 1. Okay, so now we can say c1 bilinear function of pi 1 comma pi 1 plus c2 bilinear function of pi 1 comma pi 2 equal to linear function of pi 1 minus bilinear function of pi 1 comma pi naught. So this is the first equation. Okay, so similarly for I is equal to 2, we would be getting c1 bilinear function of pi 2 comma pi 1 plus c2 into bilinear function of pi 2 comma pi 2, that is equal to linear function of pi 2 minus bilinear function of pi 2 comma pi naught. So this is the second equation. So now we can write these two equations in matrix form. Okay, so you'll write these two equations in matrix form. So if I write these equations, and we should be getting bilinear function of pi1 comma pi1, bilinear function of pi1 comma pi2, then bilinear function of pi2 comma pi1, then binary function of pi2 comma pi2, and this is multiplied by the Ritz coefficient c1 c2, which is equal to linear function of pi1 minus bilinear function of pi1 minus pi1 comma pi naught. Okay, and here linear function of pi2 minus bilinear function of pi2 comma pi naught, right? To evaluate the components, we have to evaluate individual components of this expressions bar. So we have to start with first expression. Okay, let us evaluate this bilinear function of pi1 comma pi1. So we will be getting 0 to 1 d pi1 by dx multiplied by d pi1 by dx minus 4 pi1 dot pi1 into dx. Okay. So we know that pi1 is equal to x minus x square, and if I differentiate this d pi1 by dx, I should be getting 1 minus 2x. So this is nothing but 0 to 1, 1 minus 2x the whole square minus 4 into uh, x minus x square the whole square dx. Okay. So if I expand this further, and we should be getting 0 to 1, 1 plus 4x square minus 4x minus 4 into x square plus x power 4 minus 2x cube into dx. And if I reduce this much more further, I'll get 0 to 1, 1 minus 4x minus 4x power 4 plus 8x cube into dx. So if I substitute the limits, we substitute the limit, and it should be x minus 4x square by 2 minus 4x power 5 by 5 plus 8x power 4 by 4 from 0 to 1, and I should be getting 1 minus 2 minus 4 by 5 plus 2 equal to 0 point equal to 0 point. Okay, so let us evaluate bilinear function of pi1 comma pi2. So that is nothing but 0 to 1 d pi1 by dx dot d pi2 by dx minus 4 pi1 pi2. Okay, so we know that pi2 is equal to x square minus x cube, and d pi2 by dx is equal to 2x minus 3x square. Okay. So if you substitute here, you should be getting 0 to 1, 1 minus 2x into 2x minus 3x square minus 4 into x minus x square into x square minus x cube into dx. Fine. So which is equal to 0 to 1, 2x minus 4x square minus 3x square plus 6x cube minus 4 into x cube minus x power 4 minus x power 4 plus x power 5 into dx. Okay, and if I expand this much more further, and I should be getting 0 to 1, 2x minus 7x square plus 2x cube plus 8x power 4 minus 4x power 5 dx. Okay, and if we can substitute the limits, should be getting 2x square by 2 minus 7x cube by 3 plus 2x power 4 by 4 plus 8x power 5 by 5 minus 4x power 6 by 6 from 0 to 1. Okay, and finally if I substitute, I should be getting 1 minus 7 by 3 plus 2 by 4 plus 8 by 5 minus 4 by 6, and that should be equal to 0.1. And also bilinear function of pi1 comma pi2 is equal to bilinear function of pi2 comma pi1, which is again equal to 0.1. Okay, now we can see so the first term, it is pi1 comma pi1 is 0.2, and this is 0.1. Okay, this is 0.1. So next term that we have to evaluate is bilinear function of pi2 comma pi2, that is 0 to 1, 2x minus 3x square the whole square minus 4 into x square minus x cube the whole square dx. Okay, so if I expand this, we should be getting 0 to 1, 4x square minus 12x cube plus 5x power 4 plus 5x power 4 minus 4x power 6 plus 8x power 5 dx. And if I substitute the limits, we should be getting 4 by 3 minus 3 plus 1 minus 4 by 7 plus 8 by 6, and that should be equal to 0.09523. Okay, now let us go for linear function. Okay, so linear function of pi1 is equal to minus 0 to 1 x minus x square dx, and if I expand this, I should be getting minus 1 by 2 minus 1 by 3, that is equal to minus 0.166. And similarly, linear function of pi2 is equal to minus 0 to 1 x square minus x cube dx, that is equal to minus x cube by 3 minus x power 4 by 4, 0 to 1, that is equal to minus 0.08333. Right, and if we have to find out pi1 comma pi naught also. So bilinear function of pi1 comma pi naught, that will be equal to 0 to 1, because pi naught is equal to 1 minus x, and d pi naught by dx is equal to minus 1. So our equation would be 1 minus 2x into minus 1 minus 4 into x minus x square into 1 minus x dx. Okay. If we evaluate this expression, we should be getting 0 to 1 minus 1 plus 2x minus 4x plus 4x square uh, plus 4x square again plus 4x square minus 4x cube into dx. So which we will be getting minus x plus 2x square by 2 minus 4x square by 2 plus 4x cube by 3 plus 4x cube by 3 minus 4x power 4 by 4 from 0 to 1. That is equal to minus 1 plus 1 minus 2 plus 4 by 3 plus 4 by 3 minus 1. That is equal to minus 0.3333. So that is for a bilinear function pi 1 comma pi naught. And similarly, so next one, bilinear function of pi 2 comma pi naught. So here we will be getting 0 to 1, 2x minus 3x square into minus 1 minus 4 into x square minus x cube into 1 minus x dx. So if you expand this, we should be getting 0 to 1 minus 2x plus 3x square minus 4x square plus 4x cube plus 4x cube minus 4x power 4. And if we substitute the limits, we should be getting minus 1 plus 1 minus 4 by 3 plus 1 plus 1 minus 4 by 5. So finally this answer will be minus 0.1333. Right? So if you substitute all the values in the matrix equation, so this would be 0.2, 0.1. Again, this is also 0.1. This is 0.09523, and we have Ritz coefficient C1, C2, and this should be equal to minus 0.166 minus of minus 0.333, and this is minus 0.08333 minus of minus 0.133. Okay, so if I solve this, and this should be equal, 0.2, 0.1, and this is 0.1, 0.09523, C1, C2, that is equal to, if we evaluate this, I should be getting 0.1667, and this should be 0.04997. So finally, let's find out C1 and C2. Let's find out C1 and C2. C1 is equal to 1.2025. C2 is equal to minus 0.7380. Okay. So final value will be y2 of x is equal to 1 minus x plus 1.2025 x into 1 minus x minus 0.7380 x square into 1 minus x. Okay, so that is the solution for Ritz method using for the given boundary value problem. So to summarize, Ritz method works on the weak form solution. So we should find out the weak form and evaluate each individual components of the bilinear functionals and linear functionals and substitute in the matrix equation to find the coefficients C1 and C2. Okay, thank you.